Hello students, after studying this module, you shall be able to 1. Know what are cheletropic reactions, 2. Learn mechanism of cheletropic reactions, 3. Identify stereochemistry of cheletropic addition reactions, 4. Evaluate carbene insertion mechanism in double bonds, 5. Analyze utility of cheletropic reactions in synthesis of natural products. Let us start by the introduction. An important class in pericyclic reactions belongs to cycloaddition reactions. In cycloaddition reactions, two components having suitably placed double bonds come together to form two new sigma bonds, one at each end of both components, joining them together to form a ring. Like other pericyclic reactions, cycloadditions involve a cyclic transition state and are concerted and stereospecific in nature. Diels-Alder reaction and 1,3 dipolar cycloadditions are the most important and useful of all pericyclic cycloaddition reactions. They are reversible and the reverse reaction is called a retrocycloaddition or a cycloreversion reaction. Cheletropic reactions, which fall under a subclass of cycloaddition reactions, are also a type of pericyclic reactions. The salient features of cheletropic reactions are that both new bonds are being made to the same atom but only on one of the reagents. Like other pericyclic reactions, cheletropic reactions are reversible in nature. A few illustrative examples of cheletropic reactions. The above-written reactions present examples of cheletropic addition, that is the first reaction, as well as cheletropic extrusions, because a small stable molecule is given off in the reaction, as you can see in the second and the third example. The driving force for cheletropic extrusion reactions is often the entropic benefit of gaseous evolution. For example, in the above examples, the removal of SO2, N2 and CO. The important observation here is that these small molecules that are extruded or get added to the dienes have a filled and vacant orbitals available on the same atom for bonding to other atoms, which enables them to undergo cheletropic reactions. The classical example of cheletropic addition reaction is adding sulfur dioxide to a diene. It has been shown experimentally that this reaction may lead to a 4+2 Diels-Alder adduct, which is the kinetic product but is thermally unstable and so readily undergoes a retro-Diels-Alder reaction to give back the starting material, that is 1,3-diene and sulfur dioxide. A thermodynamically more favorable addition, that is a cheletropic reaction, then takes place, which is a 4+1 cheletropic cycloaddition, leading to formation of a stable 5-membered ring adduct labeled as number 3 in the equation. In the 5-member adduct, there is proper loss of one pi bond in the substrate and there is an increment in the coordination number of the sulfur atom of the reagent, which changes to 6 from being 4 initially. There are other examples of cheletropic extrusion followed by ring closing reactions as shown. First is the thermal extrusion of SO2 leading to the formation of benzocyclobutene. The second example is that of tellurium extrusion leading to synthesis of benzocyclobutene. Next, let us have a look at stereochemistry and Woodward-Hoffmann rules for cheletropic reactions. Like all other pericyclic reactions, cheletropic reactions also follow Woodward-Hoffmann rules. The generalized Woodward-Hoffmann rules applicable to all pericyclic reactions state that in a thermal pericyclic reaction, the total number of 4Q plus 2S and 4RA components should be odd. According to rules for cheletropic reactions specifically, the linear cheletropic reactions in which the polyene is a suprafacial component, that is involving disrotatory motion of the termini, will be allowed if it has a total of 4n plus 2 electrons. But linear cheletropic reactions in which the polyene is an anterofacial component, that is involving conrotatory movement of the termini, these are allowed if it has a system of 4n electrons. These rules are reversed for a nonlinear cheletropic change. Next, let us talk about linear and nonlinear geometry. For a cheletropic addition reaction in the transition state, a small molecule donates 2 electrons towards the ring formation with the diene component. The incoming small molecule may approach the diene in a linear or nonlinear fashion, thus giving rise to 2 different geometries. To explain the linear and nonlinear geometry, let us consider the addition of a singlet carbene, CCl2 dichlorocarbene, to an alkene to make a cyclopropane ring, which is a 2 plus 1 cycloaddition. A carbene is a neutral electrophile with 6 electrons in its valence shell. Due to this, carbenes are highly reactive, where a single carbene contains an empty p orbital and a sp2 hybrid orbital that has 2 electrons. As can be seen in the scheme, in the linear approach, the carbene CCl2 with its 2 substituents lined up where they will be in the product comes straight down into the middle of the double bond. Based on Woodward-Hoffmann rules, this linear approach addition of carbene is disallowed as the total number of components is even. In the alternative nonlinear approach, in order to arrive in their proper orientation in the product, the carbene approaches the double bond on its side and then has the 2 substituents tilt towards as the reaction proceeds. In this fashion, the carbene is effectively able to take up the role of the anterofacial component. Based on Woodward-Hoffmann rules, Nonlinear addition of carbene is allowed as the total number of components is odd in this case. Interestingly, similar to ketenes, it is possible for carbenes to connect up the orthogonal orbitals of diene in an antifacial mode. Heavy carbene analogues, stannilenes, are singlet species that react with dienes via a concerted thermal 2+4 cycloaddition, which is a cheletropic reaction of the linear type allowed by the Woodward-Hoffmann rules to give cyclic products. This reaction was reported to be possible only for most electron deficient dienes to give the cyclic product. Let us now look at the application of Woodward-Hoffmann rules to cheletropic extrusion and addition of SO2, which can take place via a suprafacial disrotatory electrocyclization or an anterofacial conrotatory electrocyclization, depending on the trajectory of SO2. Woodward-Hoffmann rules and geometry for the reverse of extrusion, that is, addition of SO2 to give diene, are summarized in the following diagram. The first diagram shows a 4Q plus 2S is 1 and 4RA, the total being 1. The reaction between sulfur dioxide and butadiene also uses linear and non-linear approaches and are both allowed according to Woodward-Hoffmann rules. The former because the total number of electrons, that is 6, is a 4n plus 2 number, and the latter because the triene is flexible enough to take up the whole of anterofacial component. Now let us look at some examples of cheletropic reactions. The Ramberg-Backlund reaction is an important example of cheletropic reaction accompanying extrusion of sulfur dioxide. The reaction involves base-mediated conversion of alpha halosulfones into E or Z alkenes. Z alkenes are often observed with weak bases, whereas strong bases give predominantly E alkenes. The overall transformation is the conversion of the carbon-sulfur bonds to a carbon-carbon double bond. The diagram shows the mechanism of the Ramberg-Backlund reaction. The anionic mechanism for the Ramberg-Backlund reaction includes a rapid deprotonation, which is followed by a slow cyclization to generate a thiarine dioxide intermediate. Formation of the thiarine dioxide is followed by extrusion of SO2. The above elimination step is regarded as a concerted cycloelimination. The extrusion reaction might have a linear geometry, and this would make the loss of SO2 symmetry forbidden. Due to this reason, this step has somehow been suggested to involve a dipolar and diradical stepwise mechanisms by some researchers. Concentration of base highly influences the rate of the reaction. Thus, some facts about its mechanism, that is, whether the successive decomposition involves a rotationally hindered diradical mechanism or a concerted symmetry allowed nonlinear cheletropic pathway has not been answered until now. A refined version of the Mears modification of the Ramberg-Backlund reaction employ CbR2F2 in the presence of alumina supported KOH and tertiary butanol as solvent, which allows the conversion of alpha and alpha dash hydrogen bearing sulfones of various structural types into alkenes. An example is shown. In another cheletropic extrusion reaction, thermolysis of the substituted sulfone at 210 degrees in di-N-butyl phthalate solution generated the corresponding orthocuno dimethanes by cheletropic elimination of SO2 and led to the indicated polycycles by intramolecular 4+2 cycloaddition. The 4+1 cycloaddition between a carbene and a diene give a cyclopentene adduct. For example, heating bis heteroatom carbene and oxadiazolene give diastereomerically pure acetal in 80% yield. Annulenes are conjugated monocyclic hydrocarbons. Cheletropic elimination of CO from the product of the following cycloaddition reactions leads to formation of annulenes. Nitrous oxide elimination from nitroso-heterocyclic compounds such as shown involves cheletropic extrusion leading to formation of alkenes and NO. In the following series of compounds, the molecules 1, 2, 5 and 6 were found to be thermally stable and thus do not undergo fast cheletropic fragmentation. Rapid decomposition was observed only for nitrosoaziridine 1 and compound 5 at a temperature below 0 degrees centigrade at 45 degrees Celsius respectively. It was shown that ring strain is the critical factor for the cheletropic decomposition of cyclic nitrosamines. Based on theoretical studies, it was shown that the ring strain destabilizes the ground state of the nitrosoamines and increases the electron donor and acceptor abilities of the carbon-nitrogen bonds. This results in decrease in the activation barrier for the cheletropic fragmentation with increasing ring strain in the cyclic nitrosoamines. Further, it was also shown that the cheletropic fragmentation proceeds via a highly asynchronous transition state with a more or less planar ring nitrogen atom with the exception of aziridine system took place. In terpenes, taxanes form a large family which comprises of over 350 members, out of which the most famous one is Taxol, also called paclitaxel, which is a $1 billion anti-cancer drug. The total synthesis of taxane ring involves a cheletropic extrusion of sulfur dioxide. Lastly, to summarize what we have learned in this module. 1. Cheletropic reactions are a class of pericyclic cycloaddition reactions. 2. Cheletropic reactions are those reactions where two sigma bonds are made or broken to the same atom in the reagent. 3. Like all other pericyclic reactions, cheletropic reactions are also reversible, concerted, and include a cyclic transition state. Cheletropic extrusion reactions are the reverse of cheletropic addition reactions. These are assisted by elimination of a stable molecule from the reactant, such as nitrogen or carbon monoxide. Next, the addition of sulfur dioxide to a diene is a classical example of 4+1 cycloaddition. Cheletropic reactions follow Woodward-Hoffmann rules. According to the rules, the conjugated fragment 4n+2 pi electron systems react in a disrotatory, conrotatory mode in linear and nonlinear reactions respectively. In 4n pi electron system, it reacts in a disrotatory, that is conrotatory mode in nonlinear reaction. Next, cheletropic addition reactions involve two geometries, linear and nonlinear, based on orientation of incoming molecules relative to the diene. Next, addition of carbene to double bond is an elegant example of cheletropic addition to double bond. Ramberg-Backlund reaction is an important example of cheletropic extrusion reaction that leads to transformation of a carbon-sulfur bond to a carbon-carbon double bond. Next, nitrous oxide elimination from nitroso heterocycles are decided by ring strain in the system. Next and last, the total synthesis of important anti-cancer agent taxane involves cheletropic extrusion reaction.